Hello friends, welcome to all of you in lecture number 1 on atomic spectroscopy. Myself Dr. Venkatesh Gopala, Assistant Professor in Department of Chemistry at Anandibai Rarani Arts, Commerce and Science College, Vaipavadi. Friends, in this lecture we will see the introductory part of atomic spectroscopy. Atomic spectroscopy is the study of electromagnetic radiation absorbed and emitted by the atoms. Atomic spectroscopy is also termed as atomic spectrometry, which is the one of the oldest and most well established of analytical methods. Its backgrounds can be traced to very early observations in which the presence of a specific salts in a chemical sample reported typical color to a luminous flame. That means if you introduce the salt solution in a flame, we can see or we can observe the typical color to the flame. Atomic spectrometry is possibly the most prominent and widely used of the family of methods employed for the elemental analysis. That means this atomic spectroscopy is the most widely used for determination of elemental analysis or for doing the elemental analysis. Atomic spectrometry utilizes quantized transitions in the suitably available ultraviolet, visible, and near infrared regions of a electromagnetic spectrum. Electrons exist in energy levels, that is, atomic orbitals within an atom. Atomic orbitals are quantized, meaning means they exist as a definite values. Electrons may move between orbitals, but doing so, they must absorb or emit energy equal to the energy difference between their atoms' specified quantized orbital energy levels. Energy absorbed to move an electron from lower energy level to higher energy level, or and energy emitted as the electron moves from higher to lower energy level is absorbed or emitted in the form of a photon, that is h nu equal to E2 minus E1, that is E2 is a higher energy level and E1 is a lower energy level. So whenever an electron or an electron absorbs energy, so that energy is in the form of this photon, that is h nu. Okay, or you can say the multiple of h nu is absorbed by the electron to move or to move from lower to higher or from higher to lower. Because each element has a unique number of electrons, an atom will absorb or release energy in a pattern unique to its elemental identity, that is calcium, sodium, etc., and thus will absorb or emit the photons in correspondingly a unique pattern. The, the type of atoms present in the sample or amount of atoms present in the sample can be deduced or determined from measuring these change in light wavelength and light intensity. That means this atomic spectroscopy can be used for the qualitative and quantitative analysis. For example, when the electron in sodium gets de-excited, that means it emits the yellow light. This light produces two unique lines which appears at 8 which appears at 589 nanometer and 589.6 nanometer in the emission spectrum. These lines are called as sodium D lines, which are very intense and which helps to identify the elements. Now let's try to understand the energy level diagram of sodium. In energy level diagram, the in sodium the last electron is present in 3s orbital. So after absorbing the energy, the electron will move from 3s to 3p, 3d, or 4p. Okay, so one of the transition is possible in sodium metal. Okay, so there are three possible electronic transitions are there. The first one is the transition from 3p to 3s. So after emitting the energy from 3p to 3s, we will have the wavelength that is 589 nanometer and 589.6 nanometer, and second transition belongs to 3d to 3p. For this transition we will have the wavelength of light emission light, that is 890 nanometer. The last one is 4p to 3s, and for this transition we will have the wavelength of emission light that is at 330 nanometer. Among these three, the most prominent or most intense lines corresponds to a 3p to 3s transitions. Okay, and these lines are called as yellow D lines. So if we have these two lines in a emission spectrum, we can easily say that the in the unknown sample we will have, in unknown sample the sodium metal is present. In energy level diagram of sodium, you can see the ionization potential energy level that is at 5.12 electron volt. Okay, the next one is a energy level diagram of potassium. Now in this also the last electron is present in a s orbital, that is a 4s orbital. Okay, after absorbing the energy, the electron from the 4s orbital may move to 4p orbital, 4d orbital, or 5p orbital depending upon the amount of energy absorbed. Okay, so for this potassium we will have three electron transitions. The first one is a 4p to 4s. For this transition the emission spectrum will have the two lines, that is a wavelength of two lines, 767 nanometer and 769 nanometer. And for second transition, that is 4d to 4p, the emission spectrum will have the wavelength of light, that is 694 nanometer. And for last transition, that is 5p to 4s, the wavelength of emission light will have the 404 nanometer. That means these are the three different electron transitions. Here the electron may move from 4p to 4s, 5p to 4s, and 4d to 4p. So these are the different possibility of transitions from higher level to lower energy level. Among these three electronic transitions, the most intense lines are found to be, which are corresponds to 4p to 4s transitions. That means this potassium will have the most intense lines, which are corresponds to 4p to 4s, and these lines, that is the wavelength of the lines, are called as a red potassium doublet. Okay, so red potassium doublet lines are corresponds to the sodium, that is potassium metal. Here also the ionization potential energy, that is for potassium is 4.32 electron volt. That means after absorbing the 4.32 electron volt of energy or more, the electron from 4s orbital will move out of the potassium metal and get ionized. The last energy level diagram of calcium. Now here also in calcium the last electron is present in the 4s orbital. Okay, so after absorbing the energy, the electron will move from 4s to 4p orbital. Now in case of calcium, the only one electronic transition is observed, that is a 4p to 4s. So the emission radiation will have the wavelength of the light at 422.7 nanometer. So this is the only one line which is found in the electron transition of calcium, and which is also the most intense one. So these lines are called as a blue calcium singlet. In this case, calcium also, the ionization potential is found at a 6.11 electron volt. Okay, so that much, after absorbing that much amount of energy, the electron will move out of the calcium. Now these electronic transitions, which we have seen in three different metals, can be regulated by controlling the flame temperature by using proper fuel and oxidant gases. So that's it for this lecture. In the next lecture, we will see the flame emission spectroscopy. Thank you.